Chapter 5, Helmholtz energy and Gibbs energy. Section 5.8, Criteria of Spontaneity. The second law of thermodynamics states that the entropy of an isolated system always increases until the system reaches thermodynamic equilibrium. The second law can also be used to predict the direction of spontaneous chemical reactions or physical changes in an isolated system. Well, whatever chemical reactions or physical changes, they must result in an increase of the entropy of this isolated system. We're going to assume the universe is isolated, so all chemical reactions or physical changes, as long as they proceed spontaneously, well, they increase the entropy of the universe. The entropy change of the universe is greater than zero. There are different criteria for non-isolated systems. So if we have a closed system, that means there's no matter exchange under constant TV condition. Reactions or physical changes proceed spontaneously in the direction of decreasing A. Delta A should be negative. The Helmholtz energy must decrease when non-expansion work is zero. Here we have the proof. We start from the second law of thermodynamics. The entropy change of the universe must be greater than zero for a spontaneous process. And therefore, delta S surroundings plus delta S is greater than zero. This is just the entropy change of the surroundings. This is the entropy change of the system. And now we multiply both sides by T. We can do that because T cannot be negative. So T times delta S surroundings plus T delta S is greater than zero. And T delta S surroundings is simply Q surroundings. And Q surroundings plus T delta S is greater than zero. Q surroundings is negative Q. So we have negative Q plus T delta S is greater than zero. By the way, we just proved the Clausius inequality again. TdS minus Q is greater than zero. TdS is greater than Q. This is Clausius inequality. Actually, we just proved this one more time. Now we have this equation. Negative T delta S is less than Q. Negative Q is W minus delta U. And if the non-expansion work is zero, and in this constant volume condition, the expansion work is also zero. Alright, remember we are proving this. Delta A is less than zero for the constant TV condition. So when it's constant volume, that means there's no expansion work. And also when there's no non-expansion work, okay, this work is simply zero. And then we have negative T delta S is less than negative delta U. We move this delta U to the left hand side. So delta U minus T delta S is less than zero. And again, we're proving this delta A is less than zero under constant TV condition. When T is constant, T delta S is delta TS. And then we get this equation. And then it's just delta A is less than zero because A is U minus TS. So all this constitute the proof of delta A must be negative under constant TV condition when there's no non-expansion work. Again, there are different criteria for non-isolated systems. If we have a closed system under constant TP condition, the criterion of spontaneity is this: delta G is less than zero when there's no non-expansion work. Here's the proof. This time we're going to start with the Clausius inequality right away. T delta S is greater than Q. And this Q is Q sub P under constant TP condition. So if pressure is constant, Q is Q sub P. And Q sub P is just delta H. Now we have TdS, T delta S is greater than delta H. So delta H minus T delta S is less than zero. Temperature is constant, so T delta S is delta TS. On the left hand side, we have just delta of H minus TS. H minus TS is just G. Now we have delta G must be less than zero for any spontaneous reactions or physical changes under constant temperature and pressure condition. when the amount of non-expansion work is 0. You may ask, what if there is non-expansion work? Then delta G is less than the amount of non-expansion work. For a closed system under constant entropy condition, how do we have this constant entropy condition? So one example is adiabatic reversible. In that case, entropy is constant. Now let's look at this. Exothermic reactions or physical processes proceed spontaneously. Here we have a proof. So if we have constant entropy condition, first let's write out the Clausius inequality, which is negative Q plus T delta S is greater than 0, or T delta S is greater than Q. And then we have Q is less than T delta S. And look, it says constant entropy condition. That means delta S is 0. Therefore, Q is 0. So if you have a closed system and the system has a constant entropy condition, that means only exothermic reactions may proceed spontaneously. Now for a system under constant entropy and volume condition, chemical reactions or physical changes proceed spontaneously in the direction of decreasing the internal energy when non-expansion work is 0. So the proof is very simple. Delta U is Q plus W when there's no non-expansion work and no expansion work, because volume is constant. There's no expansion work as well. That means W is simply 0. So delta U is Q. And since Q has to be less than 0, delta U has to be less than 0. So if you have constant entropy and constant volume, and there's no non-expansion work, then not only Q should be less than 0, but also delta U should be less than 0. And that's the direction of the spontaneous reactions. For a closed system under constant entropy and pressure condition, we can easily prove this. Q sub P is less than T delta S. Again, delta S is 0, so Q sub P is less than 0. Delta H is equal to Q sub P if there's no non-expansion work, and then delta H has to be less than 0. So really, depending on the conditions of the closed system, we have different criteria for the spontaneity. For isolated system, we just look at the entropy. Entropy can only increase. We look at Helmholtz energy under constant TV condition. We look at Gibbs energy under constant TP condition. We have to look at the internal energy under constant SV condition, or enthalpy under constant SP condition. So under different conditions, we look at different criteria. So we have all those criteria on the different conditions. As you can see, we can use delta S, delta A, delta G, delta U, delta H as the criteria for the spontaneity under different conditions. Can we somehow unify all those different criteria for the system under all those different conditions? Well, the short answer is yes, but we have to define a new thermodynamic quantity, mu. Mu denotes chemical potential, and chemical potential is defined this way. The mu is delta G over delta N under constant TP condition. And why do we have I here? It's just because we need to look at a mixture. Mu sub I is the chemical potential of species I. This N is actually the number of moles of species I. And then we have delta G over delta Ni under constant TP condition. And we need to hold the amount of all other species constant. So this is how we define the chemical potential mu. For a pure substance, what is mu? Mu is simply just delta G over delta N under constant TP condition. So if you have a pure substance, the chemical potential is just the molar Gibbs energy, the same thing. But when you have a mixture, mu can be different from the molar Gibbs energy, and it's often different. Alright, and we will study chemical potential in the next section, 5.9. And then we'll realize that somehow we can unify all those criteria for spontaneity.